Hello folks, welcome to my lectures. My name is Jun, and from now on I'm going to teach the next 9 lectures. So the topics include solubility and precipitation of drugs, expiration dating, and drug stability. So first topic is solubility and precipitation. There are 2 lectures for this topic. Right now you are watching the first one. The water solubility of a drug is one of the most important properties of a drug. So why water? Why not the solubility in oil, alcohol, and so on? So that's because we human beings, as well as all of the life form on this planet that we know of, are operating on a water system. So water constitutes a basic matrix of the solvent in which all of the biological actions happens. So if a drug is not soluble in water, then it will have all kinds of problems. Efficacy can be low, it might be safety concerns, and just for this reason, if a drug is not water soluble, then a company are discouraged in developing such compound into a drug. So that's why for pharmaceutical scientists, you have to have extensive knowledge on drug solubility in water, that is. So how soluble is soluble? Well, let's see this example. So the drug solubility issue is very complicated. It's apparently drug dependent, but if we have to give a general rule, people usually think if a drug candidate's solubility is more than 100 microgram per ml, then it's considered okay. It's considered soluble. But solubility lower than this threshold are usually considered insoluble. So in this figure shows the distribution of the drug candidates. Pay attention, those are not drugs. Those are candidate compounds that could be considered for drug development. So the distribution of those compounds by the solubilities. As you can see, quite surprisingly, the majority of the drug compounds actually are in the insoluble category. So if you develop those compounds into a drug, it poses quite significant risk of failure. So therefore, for the decision making in pharmaceutical company, usually people are not favor those insoluble candidates to be developed into a drug. So what if some compounds are highly biologically active but insoluble? Well, in many cases, you can develop analog to increase its solubility. That's something we are going to talk about in this lecture. And also, I want to give you 2 bonus points which are important regarding the drug water solubility. The first one is the drug solubility is always a relative term. Relative to what? The potency of drug. So the potency means the lowest drug concentration that is necessary to be biologically active or pharmaceutically active. So if a drug is highly potent, then the dosing amount is low. You don't need very high water solubility anyway. So for such a drug, even its solubility, say, is lower than 100 microgram per ml, it might be fine because it can be considered soluble due to the high potency. The opposite can be true as well. If a drug has very low potency, you need to administrate a lot, then even its solubility is more than 100 microgram per ml, it can still be considered a drug with poor solubility. Okay? And the second point is, I'm not saying the more water soluble, the better for a drug. So in reality, for a good drug, you need to have balanced water solubility and lipid solubility. If a drug is very, very water soluble, this might be counterproductive because this drug may have adsorption issues. So in this class, however, we only talk about drug solubility. As a pharmacist, the solubility of a drug is also a very important consideration. For example, if a drug is not soluble, then the dissolution rate can be very low, which can cause low and variable bioavailability. As a pharmacist, the least thing you want is a variable bioavailability of a drug product. And due to the low bioavailability, you have more problems with food effect, and sometimes your physician might need you to deliver a drug at higher doses, but you cannot do that because of limitation of solubility. And also, often you need the knowledge of the drug solubility to solve some practical case in your work. Let's see 2 examples. The first case is related to drug solubility. So this is about a compound called niacin, which is a compound many people use to control the lipid levels. So niacin is an okay compound for this purpose, but it has one side effect, flushing, which is quite uncomfortable for many people. So a patient of yours taking this medication come to you and ask whether he should switch to the flushless niacin. He saw a good ad on the TV, but he wasn't sure about its effectiveness. There was no clear study indicating the efficacy of this form. So what would you do? So firstly, of course, you need to do some research. And shown on the left is the structure of niacin. On the right is structure of the flushless niacin. As you can see, apparently they are different. What does this mean? The second case is related to the drug precipitation. An MD resident told you that a patient's central IV line might have been clogged after infusion of sodium phenytoin in a vehicle called D5W, half 5% dextrose and half normal saline. As a rule of thumb, whenever you read about an MD resident, you should register in your mind that you are going to read about some green people liable to mistakes, and you are the one who is going to solve the problem. So don't feel too bad about those medical students, because when I was in medical school, I did a couple of teaching there. I found they do the same thing. They often talk about a junior pharmacist or pharmacist resident. So the same philosophy. But anyway, let's go back to the question. Does this suspicion has any scientific basis? If yes, what can be done to unclog the IV line? To solve both cases, you need to understand the factor determining drug solubility. This is what you will learn in this video. The extent of solubility is actually the result of the equilibrium of 2 opposite kinetic processes in a solution. So the first one being the solid drug dissolved into a solvent, and the second one being the drug already dissolved drug precipitated back into a solid form. So remember, those 2 processes are going on simultaneously. So the extent of solubility is determined by the rate constant of those 2 processes. And the rate constants are in turn determined by thermodynamic parameters of the system. So sorry guys, in order to understand the dissolution process, we have to talk about thermodynamics. I know you guys are not a big fan of thermodynamics, so I will try my best to make it simple. Basically, thermodynamics tell you 2 things. Firstly, whether a process will happen, and secondly, to what extent will it happen. In order to determine whether a process is thermodynamically favorable, we use the Gibbs free energy method. So the change of Gibbs free energy during a process has two terms, the enthalpy term and the entropy term related to the temperature. Does this make perfect sense? No? So let me explain this further. Firstly, let's look at the enthalpy term. It's pretty simple. If a process releases energy, like the going off of this A bomb, then it's favorable. It should happen. On the contrary, if a process requires energy to happen, such as cooking this frozen turkey, then it's unfavorable. Okay, so let's look at the second term, the entropy term. Again, it's pretty simple. If a process results in more chaos, like this, then it's favorable. But if a process results in more order, like this, as you can tell, it's unnatural, then it's unfavorable. So this entropy rule actually has lots of practical usage. For example, if next time your mother is criticizing your very messy bedroom, then you should argue back. You should tell her, according to entropy theory, the chaos is a law of nature. Everything goes to the chaos eventually. So since this is a law, we should obey the law. So your bedroom should stay messy. But in reality, I guarantee 99% of chance your bedroom go back to order from time to time. Why is that? That's because usually when you argue with your mother, she is likely to release a huge amount of energy upon you, making the enthalpy term really huge, which can easily override your pathetic argument of the entropy term, which is really small. So therefore, the Gibbs free energy is still favorable. So this, when it comes to your bedroom, making it in order is thermodynamically favorable. So that makes us to think, if we use this Gibbs free energy, we need to consider the combination effect of two terms. So probably, okay, so let's simplify more. So the final conclusion is that if the change of Gibbs free energy is going to the lower side, let's say if the Gibbs free energy decrease after process, then it's favorable. In another word, that means if after process the system is more stable, then it's favorable. If the system has less stability after process, then it's unfavorable. So that's why this beautiful arch collapsed 3 months after my visit spontaneously. Although that's such a unfortunate thing because it's a beautiful structure, but thermodynamically the collapse type is more stable. So it has lower energy, is thermodynamically favorable. So here we need to remember our final conclusion through this exercise. This exercise tells us if we want a process to happen, we have to create a more stable system. Otherwise, it won't happen. So translated here is that if we want to dissolve a drug into water, then the solution should be more stable than the drug or water. Otherwise, it won't happen. As I said, the thermodynamics is nothing tricky. It just gives us a simple rule of thumb to understand the world, understand the process. So here we apply this to understand the dissolution process. So we can look at the stability changes before and after dissolution. So let's suppose we are dissolving a solid drug in crystal form into water. So shown here is the structure of the crystal. You can see that in a crystal, the drug molecules are held together by ionic bonds. This is a very stable system. So what about water? So water is an extremely stable system as well. Water has a molecule weight of 18. So usually such a small molecule should be in gas form at room temperature. For example, for carbon dioxide, much bigger molecule is still in gas form. But in reality, water is in a stable liquid form, which forms the foundation for all life forms on the earth. So why water is liquid? Liquid means it's more stable than gas. That's because water molecules can form hydrogen bonds as shown here, and the hydrogen bonds stabilize the system and lower the Gibbs free energy. So water is a very stable system as well. So as you can see, the drug is a stable system and water a very stable system. They're already very stable. So in order to dissolve the drug into water, you have to top that. You have to make the system even more stable than those two. So this definitely is not an easy task. So don't take the water solubility, a good water solubility, as granted. In our everyday life, we just thought things can be easily dissolved into water, sugar, salt, and so on. But in reality, the vast majority of the compounds on this planet are not water soluble. Otherwise, when it's raining, this whole world will melt down. It doesn't happen because most of the salts or compounds are not water soluble. That's because it's very difficult to create a system more stable than what it was before the dissolution. So we come to understand that in order to dissolve a drug into water, we have to be able to do one of the two things. The first is to form hydrogen bonds. If a drug molecule can form hydrogen bond with water molecule, it can create a stabilized system which can even lower the free energy of the system. And another way is to form ions. So ions are very polar, water is very polar, so they have pretty good affinity. When the ions attach to water, it's a quite stable system, it has quite a low energy. So if a drug cannot do either of those, very likely it's insoluble. We just talked about thermodynamics, which is a very useful rule. However, it doesn't tell us everything. For example, it doesn't tell us when will a process will happen. So let's take the example of the arch I just talked about. Everybody knows eventually it will collapse, but the question is when. It's very important to know when because you don't want to stand underneath it when it collapses. So to answer such a question, we need to look at kinetics, the science of speed. So let's imagine the process of the dissolving a drug in water. So if you put a solid drug into water, at the initial stage, the rate of the dissolution is predominant because at that time there's not much drug in the solution yet. So the rate of precipitation is negligible. However, as the dissolution going, we have a higher and higher concentration of drug in the solution, and then the rate of the precipitation increases. Eventually, the rate of precipitation will be the same as the rate of dissolution. So at this stage, we call it an equilibrium. So when an equilibrium is achieved, both processes are still going on. So there are two take-home messages. So firstly, when we say equilibrium is achieved, it doesn't mean any of those two processes stopped. They are still going on all the time, never stop, and there's dynamic exchange of drug molecules between the solid phase and the solution phase all the time. So secondly, and importantly, here is a concept. The equilibrium concentration of the drug is defined as the solubility of the drug. The equilibrium or saturated concentration of the drug is the drug solubility. So from now on, when I talk about the solubility of the drug, it always refers to the equilibrium state, not any other state. I wouldn't say that again. Before we go any further, we need to ask another fundamental question. What is an adequate solubility of a drug? So everything can be dissolved in water to a certain extent, but what is a sufficient solubility for a specific drug? Well, it depends on the need, what we need in the pharmacy. So basically, there are 2 points here. Firstly, what is a proper therapeutic dose? So that's related to the potency of the drug and what concentration do we need to achieve in order to obtain desired therapeutic effect. And second point is how is a drug administered to the patients. For example, the solubility requirement for oral administration is quite different than that for IV. So according to FDA, an oral drug is highly soluble if the highest therapeutic dose can be dissolved in 8 ounces of water over a pH within 1 to 7. Not in the entire range, any specific pH you can achieve the solubility, then it's highly soluble. So as you can see, it's related to the dose and also related to the administration route. And also, this FDA definition is not absolute. For example, I give you a very extreme example, actually. So years ago, my lab was working with a pharmaceutical company called Forest Lab. They have a super potent candidate. Each therapeutic dose for an adult was only 5 nanogram. 5 nanogram. That's really, really low dosing amount. So the water solubility lower than 1 nanogram per ml, let's say a fraction of a nanogram per ml, would be perfectly fine for this drug product. So in this case, you don't need much solubility at all. So again, what the solubility need is highly related to the therapeutic doses and also administration route. Now we have the target of solubility, and then the next topic I want to discuss is the factors that affect drug solubility. This topic is very complex. Here I'll give you an example. So shown here is a box of the children's acetaminophen, the QPAP. So from the box, you can read that there are so many components in this simple drug product. You have acetaminophen, the drug itself, inactive ingredient, and dyes, solvent, co-solvent, and preservative, and sucrose, and so on. So any of those components can affect the drug solubility. So from this example, I just want to show that even for the most commonly used and the simple form of the drug product, the issue of solubility is complicated. And by the way, so that's why when we talk about a drug, we never talk about a drug. We talk about a drug product, because everything in the package can affect the property of the product. So next I will talk about the factors that determine drug solubility. So there are many factors. Apparently the most important factor is structure of the drug. Unfortunately, it's very difficult to predict a solubility just based on the structure of the drug, because A modern drug usually is a big organic molecule with many different atoms in it and held together by very complex chemical bonds. So our current technology cannot fully understand such systems. So we cannot model the features of those systems. For example, we cannot predict the polarity and spatial effects in such molecule. We do not fully understand them. But that being said, that doesn't mean we cannot use some very general rules just to estimate drug solubility in the pharmacy. So here I will introduce several such rules. The first rule is called the electronic charge rule. If a drug is salt, then it can easily form ions in the water base. So therefore it tends to be more water soluble. For example, for phenytoin sodium. So in this case, the phenytoin, the drug itself, is a negative charge. So the negative charge ions can be soluble in water. So this increases the solubility of the drug quite significantly. So in the second example, morphine sulfate, the drug itself right now is a positive charge, and this drug is quite soluble. On the other hand, if a drug cannot readily form ions in aqueous phase, for example, corticosteroids, they are not in ionic form, then those compounds are not easily soluble. But fortunately for corticosteroids, those are pretty potent drugs, so they don't need very high solubility anyway. The second rule I want to talk about is the polar atom rules. So if a drug molecule contains many polar atoms, such as oxygen and nitrogen, then it tends to be more soluble. So that's because those polar atoms can easily form hydrogen bonds with water molecule, which is a quite stable system. So if you can blend the drug into the water by forming hydrogen bonds with water molecule, you lower the free energy of the system. So if a drug has many such atoms, then the solubility can be improved significantly. So here I give you two examples. The first example is a small protein called interferon. For proteins, it contains many amino acids units. For each amino acid, it contains many oxygen and nitrogen atoms, which are highly polar and water soluble. So usually most proteins are water soluble. Of course, there are certain number of proteins which are called transmembrane proteins that may be less soluble. And another example is polysaccharide. For polysaccharide means the polymer of many sugar units. So here, this example is for heparin. Heparin is used in surgery to prevent clotting, and also is also a blood thinner. Heparin contains many units of glucosamine, so which are sugars containing both nitrogen and oxygen atoms. So heparin are very water soluble. On the contrary, if a drug mainly contains nonpolar atoms, for example hydrogen carbon, then those molecules tend to be less soluble. For example, most of the hormones fall into this category. But fortunately, for hormones, you don't need very high concentration to achieve the desired therapeutic effect. The third rule I'm going to talk about is the molecular weight rule. So it states that if a drug has low molecular weight, for example smaller than 300 Dalton, then it tends to be more water soluble. So that's because for smaller molecules, it's much more easier to get dispersed into the water system, and which achieve a low energy system. So here the example I give you is a molecules called GHB and acetaminophen. Both are small molecules, both are very water soluble. On the contrary, if the drug molecule has large molecular weight, then it's more difficult to disperse it in the water system because it requires more energy to do so. So the Gibbs free energy of the system would be higher, and therefore it's a disadvantage in terms of solubility. So let's say an example. Paclitaxel is a very important anti-cancer agent. It has been there for many years and very effective. So one issue with paclitaxel is that the solubility is pretty poor. So in the pharmacy, unless you handle it properly, it could be a disaster. So paclitaxel has low water solubility largely because it's such a big molecule. And for such a molecule, it's quite difficult to blend into pure water with low free energy. So more often than not, co-solvent is needed. But when you think about it, proteins are very big molecules, and the polysaccharides are big molecules as well. But both can be highly water soluble. So from this example, probably you can get the sense that any of those rules are not absolute. It just gives you some guidance, but you need to consider quite a number of other features or the factors. For example, for protein, although it's a big molecule, but it has many polar atoms, the same for the polysaccharide. So those overrides the disadvantage brought by the high molecular weight. The last rule I want to talk about is called the log P rules. Log P is the indicator of the hydrophobicity of the drug. The higher log P value, the more hydrophobic a drug is. So if a drug has a low log P value, then it has low hydrophobicity, and of course it has more water solubility. And if the drug have a high log P value, then it's less water soluble. So it's a very straightforward concept. In reality, you don't see many drugs has a high log P value. So that's because log P can be easily calculated by some simple tools. When a pharmacist or pharmaceutical scientist see a candidate with a high log P value, he or she would be discouraged from developing such candidates into a drug. So therefore, you don't see many drug molecules on the market with high log P value. However, there's one class of compounds usually has a high log P value, the pesticides. So in sharp contrast to the drug, the pesticides should have high hydrophobicity. That's because when you apply those to plants, you want them to stay for a while. You don't want rain or watering remove them quickly. So you want those agents to be hydrophobic. So the majority of the pesticides are hydrophobic. So shown here, the example is DDT. Over the last century, we learned that it's a really nasty compound. Okay, so that's so much for the chemical structure. So far we learned several rules. Electronic charge, molecule weight, log P, and the polar atoms. So I want to say that each of the rules are very general rules. You cannot use it to solve all of the problem. But that being said, if you compare apple to apples, those rules can be very useful in pharmacy. So let's go back and look at the case 1 to use the rules we just learned. So in case 1, a patient used niacin to control lipid levels, and he saw a nice TV ad about flushless niacin. So he wanted to switch to it, but he wasn't sure whether it's a good idea or not. You as a pharmacist are here to advise him. So of course, firstly, you need to do some research. you just look at the structure of niacin, you can see that actually it's a very nice molecule. It's small, that's a good thing because water soluble, and it has multiple oxygen and nitrogen polar atoms, another good thing for water solubility. And it's a carboxylic acid. It can form negative ion under certain pH, another advantage. So niacin can be highly water soluble, but look at the flushless niacin structure on the right. So firstly, you can see it has a large molecular weight, so that's raises a flag about the solubility. And secondly, for this molecule, as you can see, actually people conjugate 6 niacin molecules to one hydrocarbon ring. Hydrocarbon ring are totally nonpolar ring, very, very hydrophobic. So therefore, you probably should have concerns on the solubility. So in reality, some most recent study already show that for flushless niacin, its solubility may not be enough to achieve decent bioavailability. So, as a pharmacist, I hope you can advise your patients that, look, I think probably the solubility can be problematic. You can certainly try this molecule, but it may not achieve therapeutic effect. So how to solve the solubility problem? Again, using the rules we just learned, the one effective way is to change the structure of molecule. This can be really effective. For example, you can make the drug a salt or add more polar atoms to it. Although this way can definitely change, enhance the solubility in water, when risk is you change the drug effect as well, because drug effect is very complicated issue. You cannot just predict it. So you have to do lots of research from the square zero in order to characterize the drug effect. So the second way to do this is to make a prodrug. As you have already learned, the prodrug actually is the original drug conjugated to another moiety. To improve the solubility, this moiety must have two features. The firstly, this moiety or structure, the small structure that you conjugated on the original drug, should be easily cleaved off under physiological conditions. And secondly, this moiety should help with the solubility. So that's why people usually conjugate the salt to the original drug to make a prodrug if solubility is an issue. So let's see two examples. The first example is a methylprednisolone succinate. Methylprednisolone has a really low solubility, and people conjugate this succinate group to methylprednisolone. Under physiological conditions, so this succinate group can be cleaved off quite easily to release the original drug, methylprednisolone. So the pharmaceutical active form is still the same. So it doesn't change the drug effect much. The second example is on the phenytoin. Phenytoin is not very water soluble. So to overcome this problem, people can conjugate the phosphor group to the original drug, and this drug, when injected to people, it can be cleaved under physiological conditions, which release the phenytoin in the original form. So it doesn't change the drug effect either. Okay, that's so much for this part. So the next video we will talk about the other factors. Thank you.